In this question, we're going to see how we calculate the masses of galaxies. As we've already seen in this course, measuring masses is generally about measuring orbits. Earlier, we talked about how we can find the masses of stars by studying the orbits of binary star systems. We use the same idea for galaxies. By studying the orbits of the stars that make up the galaxy, we can determine how much mass the galaxy contains. We're trying to find out how much mass some of our galaxies contain and which one has the most mass. Remember that mass determines gravity, so the stars that orbit within the galaxy will be moving fast enough that they don't fall into the center of the galaxy. Hence, we'll want to use the speeds the stars are moving to tell us about the galaxy's mass. As we've seen with our own galaxy, the orbit speeds are fairly constant across most parts of a galaxy, so we can use just one speed to describe the orbits of the stars. But we also need to know the size of the galaxy. That's because gravity gets weaker with distance. So depending on the size of the galaxy, you may find a faster or slower orbit speed. The question doesn't give you any relevant numbers, so we can skip the what you know box and move straight on to the prediction. Since both speed and size can be important here, either one could determine which is the largest galaxy. You'll need to look at the numbers and try to decide which will be most important. Make sure you say why you pick the galaxy you're choosing. Also remember that if your prediction doesn't work out, it's okay to go back and revisit your thoughts on this in the last part of the question. The equation we need to use here is Newton's version of Kepler's third law of motion. This is the same calculation astronomers use to find the masses of planets by looking at the orbits of their moons and the masses of stars that orbit each other. When we're solving this for galaxies, the equation looks like this. In this form, we see that m is the mass of the galaxy, while r is its radius and v is the orbit velocity of stars within the galaxy. G is the gravitational constant. Remember that G always has the same value, 6.67 times 10 to the negative 11th power meters cubed per kilogram second squared. Make sure you write this value down along with the units in the looking up part of your worksheet. The set of units in G is important. On the next slide, we'll have to make sure that everything else has units that match up with these ones. We also need to look up the radius and velocity of each galaxy. The velocity is given on the constellation table in the galaxies section. The radius isn't there, but the diameter is. Remember that radius is 1/2 of the diameter. Pick 3 galaxies and make sure you include the galaxy you predicted would have the most mass. Finally, remember that the mass of the Sun is 2 times 10 to the 30th kilograms. We're going to need that at the end of the question when we convert the galaxy's mass to solar masses. The gravitational constant defines the units we need to use for this calculation: meters for distances, kilograms for masses, and seconds for time. The speed given in the table is in meters per second, so it fits with the units in the gravitational constant. However, the radius is in kilolight years. A kilolight year is 1,000 light years, so that's a huge number of meters. In fact, in the lecture on cosmology, we calculated that a kilolight year is roughly 1 times 10 to the 19th meters, so that's the conversion factor we'll use. Let's look at an example where the galaxy has a diameter of 120 kilolight years. That's just a bit bigger than our own Milky Way galaxy. First, we divide the diameter by 2 to get the radius of 60 kilolight years. Then, to convert this to meters, we simply multiply this value by the conversion factor, 1 times 10 to the 19th meters, divided by 1 kilolight year. That gives us a radius of 6 times 10 to the 20th meters. As we expected, this is a lot of meters. Now let's try calculating the mass of the galaxy. We'll need the velocity. Let's assume that it is 1.5 times 10 to the fifth meters per second. That's about 150 kilometers per second, just a little slower than the orbit speed in our own galaxy. So we plug all these values into the formula. The radius and the velocity go on top of the fraction and the gravitational constant on the bottom. Don't forget to square the velocity. We'll do that as a first step. Notice that the units get squared as well as the number. Next, we'll multiply the mass by the velocity squared. This gives about 10 to the 31 meters cubed per second squared. The units here are almost the same as the units of the gravitational constant. The only difference is that there are kilograms in the constant, so most of the units will cancel out in the next step. When we divide the top and bottom of the equation, we get a mass of 2 times 10 to the 41 kilograms. As a last step, we should convert this value to solar masses, since it's hard to get a sense of how big 10 to the 41 kilograms really is. So we multiply through by the conversion factor 1 solar mass divided by 2 times 10 to the 30th kilograms, and that gives us 1 times 10 to the 11th solar masses, or about 100 billion solar masses. This is a little less than the mass of the Milky Way, which makes sense since the orbit speeds were less, even though the size was a little larger. Now you should see if your answers make sense and fit your predictions. Remember that both orbit velocity and size were important for the mass. So if the answer doesn't match what you expected, first look to see if it's the one you didn't predict that turned out to dominate. Another thing to look at is whether the numbers themselves are reasonable. Remember, we're looking at a galaxy here. So if the numbers you're getting are much less than 10 to the 9th solar masses, there's a good chance it's too small. On the other hand, even the largest galaxies rarely get bigger than 10 to the 13th solar masses, so larger values in this would be suspicious as well. If you're getting numbers that don't look right, make sure you go back and check your calculations. And if you're not sure what's wrong, feel free to ask for help.